Hi everyone, my name is Albert Chiu, and today I'm going to be giving a talk entitled Bayesian Rule Set, a quantitative alternative to qualitative comparative analysis. This is work that's joint with Yiqing Chiu, who's an assistant professor at the Department of Political Science at Stanford, where I'm also currently a graduate student. And so I'm going to start with this motivating example drawn from modernization theory, which posits that some complex interaction between variables like wealth, industrialization, education, and urbanization work together to help produce democratic consolidation. But from a theory building point of view, we might be asking which of these variables matter and for whom do they matter? So for example, maybe wealth is a really good predictor for whether a country is going to consolidate, democracy is going to consolidate, but only for certain countries, like industrialized countries or highly educated countries. And this is closely related to the literature on heterogeneous treatment effects in the causal inference space. But perhaps surprisingly, the most popular class of methods in political science, regression, is actually quite ill-suited for this task. Regression is a really big class of methods, but all these methods share in common the assumption that effects are marginal and constant. And so by marginal, I mean that we're focusing on just one variable at a time, holding all else equal. And by constant, I mean that we're assuming the effect doesn't depend on other variables. We can relax these assumptions, but it comes at a cost. The most popular way of doing this is using multiplicative interaction terms, but the problem is that this model quickly becomes uninterpretable. So here, even with just 3 variables and a third order interaction, it's hard to understand what the substantive implications of this model are. And also, we quickly run into dimensionality problems because the number of terms is exponential in both the number of variables and the order of interactions. And so very quickly, we're going to have to start picking which terms we're going to include using something like the lasso or elastic net. But these methods are not very good at inducing enough sparsity for the models to be interpretable. And so an alternative way then of describing the data is using what are called rule sets. These are if-then statements that classify data. So for example, if a country is high wealth or a country is medium wealth and low industrialization, then we're going to predict that it's going to be a stable democracy. And this is actually the rule set you get when you use a method called Qualitative Comparative Analysis, or QCA, on a data set of interwar European countries. QCA is a popular method in sociology, political science, and some other social sciences. And to give you a graphical representation of what this looks like, here we have encircled the points that are covered by the rule set. And by covered, I just mean that it satisfies the rule set. So here, the solid line encircles countries that are high wealth, and here the dashed line encircles countries that are medium wealth and low industrialization. This plot is just a 2D representation of some higher dimensional data. These axes don't actually mean anything. But the point here is that the points we circle are the points that we're going to classify as positive, and everything else we're going to classify as negative. And the problem, though, is that QCA was only really meant to handle these small n data sets. And when you get into larger n data sets, errors become inevitable, and QCA doesn't really know what to do with them. And so by errors, I'm specifically referring to when observations have the same values for covariates, but different outcomes. And when this happens, QCA just starts throwing out data, because again, it doesn't know what to do. There are some fixes that have been proposed, but none of these really solve the core issues, and all of them still continue to throw out data. And another problem is that QCA tends to pick these really complex rule sets that are uninterpretable and overfitted. Because what it likes to do is it likes to pick these rule sets that explain your specific sample very, very well, but then they generalize quite poorly. And they're also way too complicated for you to understand. And lastly, QCA quickly becomes computationally infeasible, both because the number of variables grows exponentially, or sorry, the size of the problem grows exponentially with the number of variables, and also because the fastest way we know how to solve QCA still takes exponential runtime. So given the utility of rule sets, but the inability of QCA to find useful rule sets in some settings, we might be asking if there's another way to find these rule sets. And so there's actually a number of ways. One of which you may already be familiar with, decision trees can actually be one way of recovering rule sets. Random forest is not, because when you bootstrap aggregate or bag, you're no longer able to recover rule sets from the model. But I'm going to tell you there's actually a different and better way called Bayesian rule sets. And so this was proposed by a group of computer scientists a number of years ago. And it's nice because it doesn't suffer the same drawbacks as QCA. So it's compatible with errors. It doesn't throw out your data. It maintains sparsity and parsimony in any setting, and it's computationally feasible. And the reason we prefer it to decision trees is it's actually better at preserving sparsity and parsimony, by which we mean there's few rules and each rule is of a short length, which makes the rule set more interpretable. And for a given sparsity or parsimony, it tends to do a better job at classifying the data. There are still some remaining problems with BRS, but we're going to propose some ways of improving it. These pertain to its priors in particular and the way we specify hyperparameters. And we're also going to propose a number of ways at improving rule set-based methods in general. These are going to be ways to quantify uncertainty and to stabilize results, and also a set of graphical tools that you can use with rule set-based methods. Now that I've hopefully convinced you that rule sets are this useful way to represent data, and that QCA is incapable of finding rule sets in certain settings, I'm going to explain BRS in more detail as well as their contributions to their methods before giving you some ideas about how we can improve rule set methods in general using the bootstrap. After that, I'm going to introduce a set of graphical tools we've developed specifically for rule set-based methods. And then I'm going to back up my earlier claim that QCA doesn't perform in certain settings, in particular large N, large P, heterogeneous data settings, before giving you an example of this type of setting where rule sets recover this really interesting description of the data that regression doesn't already recover. And so the basic setup of BRS is that we want to find a rule set that maximizes the posterior distribution given some hyperparameters and the data. And so again, rule sets are these if-then statements that classify data. But another way of thinking about them is in terms of set membership. So you can just replace the and with an intersection and the or with a union. And then you can treat a rule set as some subset of the positive class. For this method to work, we're going to need a binary outcome and discrete data. And we're also going to have to give it some hyperparameters. And I'll tell you more about how to choose these in a little bit. The reason we want to maximize the posterior is we're going to use a prior to control sparsity and the likelihood to control performance. And the posterior melds these together. And so the likelihood of one point being classified as, having positive outcome is going to be distributed Bernoulli, conditional on whether it's going to be in the rule, part of the rule set. And the probability is going to be drawn from beta distribution with different parameters depending on whether or not it's in the rule set. And so we can choose these parameters such that the model rewards correct classification and penalizes incorrect classification. The likelihood, so BRS actually has two sets of likelihoods. The original version uses a type of beta, the prior. The original version uses a beta prior, but then a later paper by the original authors proposed a type of Poisson priors. There's still some issues with these that we're going to address, and we're going to improve upon them slightly. But the basic idea is that our prior on the data generating process is that nature picks some number of rules from a Poisson distribution with a parameter that we choose. And then for each of these rules, nature is going to pick the length of that from a truncated Poisson, again with a parameter that we're going to choose. And it's going to be truncated from 1 up until some pre-specified maximum length. The original formulation by default sets this to the maximum number of variables, but this induces a lot of uninterpretability and computational infeasibility. So we're going to limit it to a much smaller number. And then for each of, for 1 through the length of each of these rules, we're going to randomly pick the variable as well as that variable's value. And then we're going to take their intersection to form a rule, and we're going to take the union of these rules to form a rule set. And then, as I mentioned before, the user gets to choose hyperparameters, and it tells us how we're going to trade off between parsimony and sparsity. And the reason we prefer the Poisson version of the priors over the beta version is because it induces these really well-behaved penalties. In particular, they're positive over a particular subset of the rules parameter space, and they're strictly decreasing functions of just one of the parameters. And so again, before we had lambda and eta, but we can actually, as it turns out, fix lambda to be some number and then just manipulate eta. And we can keep decreasing it if we want to penalize complexity more. And so this reduces a really complex search over a number of hyperparameters, or at least in the case of the beta priors, it would be a number. In the case of the Poisson priors, it's just 2, but still it reduces this grid search into just a linear search, which is really nice for hyperparameter tuning. And then on the reverse, if the rule set is too sparse, that is, you're willing to trade off some sparsity, some complexity for better performance, then instead of moving your hyperparameters outside of the bounds we derived, which instead of penalizing complexity would actually reward complexity, we suggest you strengthen the likelihood. That is, tell the algorithm we care more about performance. We needed to do better. And you can do this by multiplying the associated hyperparameters by some constant greater than 1. I'm not going to spend too much time on the algorithm for actually finding the rule set, but I just want to flag that it's an enormous search space, which makes, in general, rule set methods quite difficult. But the nice thing about BRS is that Wang et al. Provide these bounds that significantly reduce the search space. The intuition behind these bounds is that we can only use a few rules to cover the entire positive class, and so each of these has to cover a large number of cases. The exact algorithm for inference requires you to update this rule pool at each step, but this is kind of computationally expensive. And so they instead propose a quote unquote approximate algorithm that instead just calls the rules at the beginning using some arbitrary cutoff, and then uses that same pool of rules throughout the rest of the algorithm. And this is good enough for us because we don't actually really care about whether it maximizes the posterior. That quality in and of itself isn't very valuable. Rather, we just care that the rule set is both sparse or precipitous and that it's high performing. And to the extent that it's both, which typically with the approximate algorithm it is, we're content. You can use any type of search procedure with these bounds, but Wang et al. Specifically use a type of simulated annealing algorithm, which is nice because it balances greediness with exploration to help avoid local maxima. And we're just going to continue using their same algorithm because it works pretty well. And so there are, again, some remaining challenges for rule set-based methods alone, not just BRS, one of which is that it's really difficult to quantify uncertainty. So the natural way of quantifying uncertainty in regression is using something like a confidence interval or a credible interval. And you might think that the analogy for rule sets is then to use a credible or confidence set or collection of rule sets that satisfies the same probability bounds. But there's two problems here. One of which is that there's many collections of rule sets that satisfy these bounds, and you want to arbitrate between them, perhaps by picking the smallest such set. But then this would require calculating a posterior over very many rule sets, sorting them, and this is just computationally infeasible. And the second is, even if you do find that good set collection that satisfies your probability bounds, it's going to be really hard to summarize them. Using endpoints, you can summarize an interval. You can tell me the minimum and the maximum, and I'll intuitively know what that means. But you can't do the same thing for a rule set because there's no such thing as ordering for rule sets. And so what you're instead going to have to do is essentially list every single rule set that's in the collection, which just doesn't make any sense to anyone. And so we're going to propose an alternative way of quantifying uncertainty using the bootstrap. We're going to define two terms here. One is prevalence, so that's the proportion of times a rule appears in a solution when you bootstrap the data. And the other is coverage. That's the proportion of points covered by a rule. And so the first version relates directly to the bootstrap. So you're going to sample with replacement and use your rule set-based method on each bootstrap sample. And it's going to give you some rule set. You're going to disaggregate that rule set into different rules, and then you're going to plot them. Or sorry, you're going to count how many times they appear. And then coverage doesn't relate directly to the bootstrap. You can calculate coverage for just one particular sample, but you can use the bootstrap to give you these frequentist confidence intervals. And what that tells you is that it gives you this sense of uncertainty in that if the confidence interval for coverage includes 0, we might think that maybe the rule is just spuriously appearing in our rule sets. And so you can plot prevalence. For example, here on the left, we have prevalence. You can also plot coverage. On the right, we have coverage. And you can plot also the 95% confidence intervals for coverage. And so we see, for example, that for these two rules, the confidence interval for coverage actually includes 0, which again, might give us an idea that these are just spuriously significant. They're just in our rule set because we got kind of a bad sample. And then another problem with rule sets is that they can be a little bit unstable. And more importantly, the consequences of instability are more pernicious for rule sets than for a regression. So for regression, a small change in your slope doesn't really mean much, but for a rule set, it can have some substantive implications. This instability might be due to a failure of the algorithm to converge. So again, it's a very difficult, very large search space. And it also might be due to perturbations in the data. So just small changes in the data that give you slightly different results. And so the solution we're going to propose is to aggregate high prevalence rules into a rule set. By aggregate, we just mean take these rules and then take their union to make a rule set. And you're going to pick a rule set based on some criteria based off of both performance and sparsity. The one we're going to be using is we're going to maximize accuracy using at most 3 rules. And so if we do that, it ends up that the rule that does best on this criteria is the same rule that QCA picks out. So in a sense, BRS with aggregation recovers the same rule set that QCA does, at least for this small n example that I introduced at the beginning. And so the rules that are highlighted in a darker color here are the rules that the aggregation method picks. Another way of representing this rule set is using something called a chord diagram. So the orange chord here represents one rule, high wealth, and the blue chord here represents another rule, medium wealth or low industrialization. And lastly, as you've seen this before, this is a low dimensional representation of higher dimensional data. In particular, we're using a TSNE algorithm to reduce the dimension of the data. And it works quite nicely here. It carves out these 2 distinct clusters of points, each covered by a different rule. And so we're going to use color to code positive outcome or negative outcome. Green is positive, red is negative. And we're going to use circles and X's to denote whether an observation was correctly or incorrectly classified, respectively. And so we see here that the method does quite well, actually, at covering almost all of the positive class. There's just one point here that the rule set does not correctly classify. And that's a positive class that it fails to cover. And as I promised before, I'm now going to give you a little bit of evidence for my earlier claim that QCA doesn't really do that well once we leave this very small n deterministic almost setting. And so in our simulations, we're going to vary both the sample size and the number of variables. And then we're going to have a binary outcome that's either deterministic or probabilistic. If it's deterministic, then we're going to say that the outcome is going to be positive if and only if it's in the true rule set. The true rule set here being this. So if it's either both V1 and V2, so in the set V1 and V2, or it's in the set V3 and V4 and the complement of V5, so it's not in V5. And if it satisfies either of these rules, and we're in a deterministic setting, then it's going to have positive outcome if and only if it satisfies this rule. Alternatively, we're going to have a probabilistic setting where even if it is part of the true rule set, there's going to be a small chance, a 25% chance that it's still going to have negative outcome. And if it's not in the true rule set, there's still going to be a small chance, a 25% chance that it will have positive outcome. And so we see here that in a deterministic setting, QCA and BRS basically perform the same. So on the left here, we have the number of rules. So how many rules are in a rule set? In the middle, we have the average length of rules. So how many conditions are in each rule? And the right, we have out of sample accuracy. And again, BRS and QCA both do similarly and both basically recover the true rule set, at least for a large enough sample. If we increase the number of variables slightly, the story is similar. It just takes a few more data points for them to converge. QCA doesn't do too well, but again, for a large enough sample size, it does fine. The problems really start to emerge when you have probabilistically generated outcomes. And so we see here that even for just 5 variables, QCA is already starting to pick out rules that are a little bit too long and a few too many rules. And as a result, it's getting a little too specific to the particular sample and not performing as well as the true rule set. So the true rule set would have about a 75% out of sample accuracy, which BRS attains in the limit. And this problem worsens when you give it more variables. And so with just 10 variables, we already see that QCA completely loses interpretability. And this is a really concerning property because what we're seeing is that actually, as the sample size gets larger, QCA is getting further and further from the truth. And it's not even recovering something that closely resembles the true rule set in performance. It's actually quite underperforming, even though it's pretty, or actually rather because it's picking out these highly specific rules. Whereas BRS, on the other hand, maintains parsimony and also gives us a rule set that performs at least almost as well as the true rule set as the sample set size gets larger. And now I'm going to give you an empirical example from this type of large N large P setting where outcome is generated probabilistically. And so this is going to be using data from a study published this year that originally uses regression to estimate the effect of depression on voter turnout. So regression is fine when you have a specific variable in mind and you want to estimate its effect, but it doesn't do so well at the alternative task of theory building or discovery. So when you don't have a particular variable in mind, and you're instead just interested in the more general question, who votes and which variables are predictive for voter turnout and for whom are they predictive? And so I'm going to show you this bar plot of the bootstrap rules. And we see here that age is actually a really good predictor of voter turnout. So if the individual is high age, we're pretty confident that that person is going to vote. It doesn't matter what other characteristics they have, we're pretty confident that they're going to vote. So age also appears in a number of rules of length too. So we can perhaps refine that set a little bit. So we can do a little bit better at predicting if we know a little bit more about the individual. But we see that the variable that age is interacted with changes depending on the sample, indicating that perhaps these relationships are just sort of spurious and other variables don't actually give us that much more information when we already know that the individual is high age. And if we go to the aggregated rule set, again, high age is part of this aggregated rule set, but the other rules are first, high political interest and high income and not Black, or high political interest and low depression or medium. Sorry, high political interest and lower medium depression. And so one interpretation of this is, again, that high age alone is very predictive. We don't really need to know more about that individual. We're pretty sure they're going to vote. But amongst younger voters, as it turns out, about 55% to 45% vote or don't vote. And then political interest turns out to be quite an important predictor for these people, but not good enough. So it turns out that only about 65% of young voters, or sorry, young respondents who say they're interested in politics don't actually vote, and then the rest don't. And as it turns out, there's specific classes of people for which high interest in politics is insufficient. And so these are people who are either depressed or people who are facing certain racial and class barriers to voting. And here we have a graphical, again, 2D representation of our data. And we use this dashed line to circle points covered by just one rule. In particular, these are low or medium depression and high political interest. It's not all clustered together. It's not quite as nice as the first TSNE plot I showed you, because this is much more high dimensional data and there's also many more observations. But what this plot does tell us is that there's actually quite a few points that are misclassified. This rule set already does a really good job at classifying the data. There's just these few clusters of X's of incorrectly classified points. And it also reminds us that rule sets come with diminishing returns. So we're already doing such a good job at classifying the data that in order to classify it more points correctly, we're going to have to incur significantly more complexity for very little gain. And so, for example, perhaps we could extend the rule set to cover this cluster of points, but that's going to require us to add a lot more complexity to the rule set for just a relatively small gain in performance, just this class. And perhaps in the process, we will also cover some points that we don't want to cover. And so lastly, I'm going to conclude by again saying that rule sets are this very useful way of interpretably representing complex relationships in data. It does a better job at regression, which has a difficult time discovering relationships in data and building theories. And the QCA, which is this method that political scientists have been using to learn rule sets, fails in certain settings, when data is large and heterogeneous in particular, whereas BRS solves some of UCA's problem and succeeds in these settings. There's still some remaining problems to BRS, but we propose solutions to some of these. So for example, BRS's priors and hyperparameters induce a bit of computational intractability and issues with interpretation or ease of use. And we come up with a way to get around this issue. And also we come up with some improvements to rule set-based methods in general. So we come up with ways to quantify uncertainty and to stabilize results, and as well as a set of graphical tools to help people represent data using rule sets. The results from rule set-based methods as well as their data. And lastly, I'm going to thank everyone for listening to this talk. And that's it. Thank you. Goodbye.